Okay, so the fundamental theorem of arithmetic is kind of like our division algorithm statement. If we just extract what we're trying to do, we're trying to prove an existence of a factorization and then prove the uniqueness of that factorization up to a reordering. So it's we generally say that theorems like this are existence and uniqueness theorems because you have to do two things. You have to prove such a thing exists, and then you have to prove that whatever you did is unique. Um, the proof of this is going to be very similar to in style as our division algorithm proof. Namely, we're going to prove that we have a factorization, and then we're going to try to do some work to show that if we had two factorizations, they actually had to be the same up to reordering. Okay, so that's the uniqueness part. For this first video, though, we're just going to prove the existence, and the next one will do uniqueness. So we want to show that if we have any natural number bigger than 1, it can be expressed as a finite product of prime numbers. That is, this should say unique primes. Well, there exists distinct primes, actually. So our P1 through Pm are going to be distinct. And exponents R1 through Rm such that n is P1, R1, P2, R2, and so on. All we're doing is if P1 shows up a bunch of times, we just collect all of them into one prime power. Okay, so the primes here is a typo, it should say distinct. Okay. So let's get started, and we're going to proceed here by induction, and we are going to do strong induction. Strong induction is very similar to induction, where you sort of assume that it's true for, in the inductive step, all previous steps. So anyways, let's get started with that. The base case is the first natural number that's bigger than 1. The first natural number that's bigger than 1 is 2, and 2 is certainly prime, because the only divisors of 2 are 1 and 2. Great, base case is done. Now what we're going to do is we're going to show that any number less than or equal to, let's just say less than or equal to n, is either prime or can be written as a product of primes. Okay, so that's our strong inductive hypothesis. And then we're going to go to the next natural number. The next natural number is n plus 1. If n plus 1 is prime, then we're good. N plus 1 is equal to just n plus 1, and that's its prime factorization. Otherwise, it's composite. So if it's composite, there is some s and t that are bigger than 1 and less than n plus 1, such that n plus 1 is s times t. Well, s and t are numbers that are certainly less than or equal to n because they're less than n plus 1, so we can apply the inductive hypothesis to s and t. The inductive hypothesis says that the theorem should be true for s and t, so they're either prime or a product of primes. But n plus 1 is s times t, so if they're prime, well, n plus 1 is a product of primes. And if they're a product of primes, then n plus 1 is still a product of primes because it's just the product of each of them. And if one is prime and the other is a product of primes, well, it's still a product of primes. So in any of those cases, n plus 1 is going to be a product of primes, and we're done. Now, the powers that you get here arise by just collecting the common primes to, if 3 shows up a bunch of times, you collect all the 3s that show up in the list. So collect common primes to get that factorization with the exponents. And that's the uniqueness, or sorry, that's the existence proof. And again, we use strong induction here. Strong induction is where you do a base case, and then your inductive step is you assume it's true for all instances less than or equal to n, and then that you try to show implies n plus 1.